Where is everybody? It's 10:30. Thank you for showing up on time, those of you who are here. Let's see, a couple of things at the beginning. So I think we're talking about a cool topic today, by the way. I really like this topic. It's kind of fun and interesting and like powers the world these days, all since like the 1800s, so it's kind of cool. Saw a lot of people in office hours yesterday when I kind of snuck in for a few minutes. How's the assignment going? Yeah, I'm hearing a little this and that. The biggest thing about this assignment is understanding those three types of registers, set, clear, and then the level one, and then understanding how to do bit shifting and bit masking and that sort of thing. And if you can do all that, I think then this assignment doesn't get doesn't end up being too bad if you can figure those parts out. So stop by office hours some more, put more questions on Piazza if you've got them, and we will go from there, and hopefully it'll be all right. But like I said, today's topic is cool. It's communication. It's basically how do we communicate either between devices or in general. This idea goes back a very, very long time, right? And it's basically communicating over space without having two people like come together and like talk, right? And here's, I guess before that we had like light signals and things like that where you could send light signals, and there were some of these ideas as well. When we talk about communications in kind of the modern age using electrical sort of situations, what are we talking about? We're talking about like the telegraph, right? Remember the telegraph, which was basically a wire, and you have a little bit of electric kind of, it's not even electronics really. It's basically you've got a key that connects to ground, and you push it down, and a relay actually changes the voltage, which ends up on the wire, and then somebody on the other side of the wire, actually the relay over there, also like reacts to that, and then you get like a beep, or you get a dit or a dot or a dash or whatever. You get that out of there, and you can send like different codes this way. And this is the way the telegraph actually worked. And it's from the mid 1800s, and it was actually an amazing development. Was this idea that you could send a signal in the end across the Atlantic Ocean, for instance, and you could instantly talk between the Queen of England could talk to the President of the United States, and it was like instantly, and that was like the biggest deal ever, right? Because this had never happened. This had never happened before. You wanted to send a message to England, if you were in New York or Washington D.C., it was 3 weeks later you would get it, right? But once the telegraph came on, and they figured out how to do undersea cables, that was the other big thing. The biggest thing there, believe it or not, turns out that, well, first of all, they didn't know how to. They were very poor at insulating wires. So they would do all these wires, lay them under the ocean, and then they would deteriorate, and then the signal would be bad and whatever. And they also had to amplify the signal. And then the other big one was, it turns out that, I don't know if you guys know that sharks have kind of electrical sensors in their like snout sort of thing. And snout, I don't know if that's the right word for a shark. But anyway, they had those, and they would go down and they'd look at this wire and go, oh, that looks tasty, and then bite it, and then they would break. So lots of issues they had to solve, but this was like a cool idea. And today we're going to talk about some of the ideas of how do we actually send a signal a little bit more efficiently than the telegraph. But let's start with the telegraph. Okay, you guys have all heard of Morse code before, right? Morse code is this idea of dots and dashes, or you could call them dits and das if you're a Morse code reader and whatever. You want to do it a little faster, it's easier to say dit and da for that. But a dit, or a dot in this case, is a single 1 unit length thing, and then a dash is actually 3 units. Okay, and there's some other interesting parts to this. The space between the parts of the same letter is 1 unit, however you're defining that unit. Okay, so if you're doing the space between the parts of the same letter, so if you did A, which is dot dash, you'd have dot, which is a certain amount of time. That same amount of time between the next part, and then the dash, which is 3, and then after the letter, you have the space between letters is 3 units, the same length as a dash, and then the space between words is 7 units. Okay, and so this is like quantified this way, and this was the signal. And the interesting thing about this signal is they were a little clever about it. You guys remember doing the Huffman encoding in 106B, if you took 106B, right? Notice that the things that are short like E and I and T, whereas T's one dash, right? Why are they short? Because they're the most frequently used, and you could actually send things faster that way, right? You're not sending too many Q's, right? Because English doesn't have any Q's, so we can make it a nice long one. So this is not as efficient as Huffman, but it's pretty efficient, and Morse and the other people who kind of quantified this came up with some ideas that were kind of interesting. Okay. So let's actually do some of this like in code right now. Okay, what we're going to do is we're going to go from our Blink program, and I'm going to show you a slightly different version of our Blink program using some of the code that you guys came up with this week, actually. Let me make this window bigger so you can actually see the details here. Maybe a little bigger. There we go. Okay, blink.c. Take a look at this blink.c here. Okay, we've got what? We've got something highlighted there. There we go. We've got pound include GPIOH. Ooh, you guys are writing all those functions this week, which is great, right? We've also got a timer function. Okay, so you know how we were talking about like the looping and doing, yeah, actually, you want to turn the, it's probably a good idea. No, I don't know. You can do them all, and I'll that one's a little better. Yeah. Okay, so in this case, the timer is a couple of functions that are that actually use the hardware timer built into the Pi to count like real amounts of time. We're not just kind of making up numbers and doing a loop to try to figure this out. It's actually querying the Pi and saying, has this timer updated, and then it's doing a loop that way. So it's actually going to be much more regular and it's going to give us numbers we can actually deal with in terms of seconds and milliseconds. So that's actually nice. That's what that's doing. And in fact, this case, second is 1,000. Okay, let's take a look at what we've got here. Okay, we've got, we're going to set our pin to 20. That's one we've seen before, right? And then we have to do a couple initializations. We initialize the timer, we initialize the GPIO pins, and then, oh, seen this function lately? Right, set output. So it's going to set the it's going to make the pin an output pin. Okay, so that's actually nice. And then we're just going to do this. We're going to do GPIO write a 1. We're going to timer delay. That's another function that does the actual delay for 1 second. That's 1,000. This timer delay in milliseconds, 1,000 a second. And then we're going to write 0, and we're going to delay again for a second, and then that's it. And that's our blink. So far, so good. So hopefully that should be what we expect. So let me see. There we go. Okay, make install. If we do this, if I do it correctly and everything's working, it should do. Okay, so I realized the other day some of you guys can't see the little light here because you're like in the back and it's on the table. So what I did was I made the world's tallest LED, and I just soldered some wires on here. So I'm going to actually switch it here. So you guys can see this. Let's see. There, and then there, I think. Uh-oh, is it? Oh, where'd it go? Oh, no, where did I just, oh, sorry, wrong one. So what happens when you don't do that? There we go, and see if that, there we go. Oops. There we go. Okay, now can you see it? Right, now it's way up tall, and you can kind of see the lone blinking light here. Okay. So that was our blink program, and it was just basically wait a second, blink. Let's turn this program into a program that will actually do some Morse code. Okay, let's actually do the SOS. Now, who knows what SOS is in Morse code? Yeah.
Dot, dash, dot, dot.
There you go. Dot, dash, dot, dot. Why is it dot, dash? Because S is dot, and O is dash, and then dot. People always do it wrong. They always do dot, dash, dot, dash. It's not. It's actually dot, dash, dot, dash. Anyway, that's the way it's supposed to go. Okay, people always do it wrong, like in the movies and things. I don't know why they do that, but that's the way it goes. So let's actually look at this. SOS dot. I think this is. Hang on. SOS.c. There we go. Okay. So if we want to do this, we're going to do this in kind of a way that actually I think is. We're going to try to do it in a way that makes it fairly general. Okay, we're going to, what's the term we use in 106b when we want to break things up into different functions and things? Decompose it, right? We're going to decompose it into a couple different things. Okay, so same sort of stuff as up top here, okay? And let's actually write a couple functions. Let's write a dot function, and let's write a dash function. right? And what we're going to do is we're going to basically blink the light in the pattern that we want for a dot or a dash. Okay, so what is a dot? When we're doing a dot, what do we have to do to the light? Let's pretend it's already off. What do we do with it? Turn it on, right? So we do GPIO right, and then we're going to just use one pin in this case. We probably could have passed in the pin, but that's all right. Okay, we're going to turn it on. Okay, then we do what? While it's on, what do we have to do? We have to wait, right? Timer delay ms, and I've actually defined a function here called delay Morse, which we're going to do 1 second, 1/6 of a second for each function there, okay? And then we're going to delay Morse, okay? And then that's going to be one dot in this case, okay? So it'll be a dot there. All right, then what do we do? Did I spell it wrong? Thank you. Okay, then what do we do? Once it's on, we do what? Turn it off. GPIO right, pin 0. And let's actually put the delay in there after an inner character spacing anyway. We'll take care of the details here. You could probably think of a different way to do this if you wanted to. MS delay Morse again, because it's one character for that. And that's it. Isn't that our dot function? I think that's good. Okay, how about the dash function? It's going to be pretty similar, isn't it? Trying to do a fancy thing. There we go. It's going to be pretty similar, like that. Except what's the only difference going to be?
3 times 1.
It's going to be what?
3 times 1.
3 times the delay. Done. Right? There's our dash function. Great. Okay. So now we've got that. Let's decompose this a little bit more. Let's actually have a function called Morse letter that actually prints out a Morse letter, and we're going to give it a letter. And we're going to give it a letter in terms of a string, which we're going to talk about at the end of class a little bit today. So how about this? Morse letter. Okay, and then I'll just call it the code, like this. And I'll make this go down here like that. Okay. And so this is going to be, we're basically going to walk through the characters in the code, and we're going to pretend this code is a string, which means it's got a null terminator on the end. We're going to talk about that at the end of class a little bit today as well. Okay, and so let's do this. Let's say that the code should be in the form. Let's call it dot dash dash dot dash dot dot dash whatever, like that. That makes sense? That's how it's going to come in. Okay, what do we have to do for this? We have to walk through it. Okay, so let's do this while we'll use some pointer arithmetic here. Code. Do this in a nice C type of way. Okay. We are going to look at the code, okay? And let's actually do a little if statement, but we'll do a fancy C type if statement, a ternary if statement. How about this? It's code plus, watch this magic here. This is terrible like style probably, but colon or question mark, and then we're going to do dot colon dash. What the heck does this mean? Right? What does this mean? This means, okay, we're looking at the character at code, and we're saying, okay, is it equal to? We'll do the plus plus in a second. Is it equal to a dot? We're going to call dot. Otherwise, it's going to be dash. So far, so good. That's what this actually is, nice and compact like this. And then the plus plus means that we increment code after we do that. We get its value there. So that's it. So this is like a lot of times you'll see C that looks like that. It's not necessarily that it's concise. It just might not be the best in the big picture. Okay, so what happens after the letter? What did we say we did after the letter? Let's see. What do we say after letters? What do we do? Space between letters is 3 units. How much are we going to delay down here? Yeah, timer delay, milliseconds, right? Delay Morse times 2. This is a good place for a comment, right? Space between letters, and then maybe +1 for space after the dot or dash. Something like that. Okay. All right, anything else? That's Morse letter. Great. Now we can do our individual letters. we could actually do this. We could probably decompose this even better, but let's just do this. Let's do a Morse S. All right, do a Morse S. What are we going to do? It's a one-liner. Morse letter, and what's the letter for S? dot, dot, dot. Done. Kind of nice. Easy one. How about we do Morse, we'll do a Morse O. Whoops. There we go. Morse O, which we're going to change this to dash, dash, dash. Done. Okay. All right. All right. And then let's see. Now we have to actually flash SOS. So we're going to do while one. And what are we actually going to send? Yeah, go ahead. We'll get there. Because right now we have to do a word, right? We're going to flash SOS. So let's do that. How do we do? What's the first thing we do? Morse S, right? All right, and then a Morse O, and then a Morse S. Now what do we need to do? Yeah, we need to do a timer delay, MS. And then this one now, how long are we going to do this one for? I think it said 7 between, right? Yeah, so we've already done 3 because of the space between the letters, right? So then we're going to do times 4, and then there's another one where we're like pause between words, something like that. Sound good? All right, let's try it. Make. Let's just see if we did it right. Oh, so far so good. Okay, I will reset my Pi to be ready to accept input and make install. And oops, oh no. Install error, wait a few seconds. This happens on mine every so often. There we go. Dot, 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 and then wait, dot, 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 dash, 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 dot, dot, dot. Now the Coast Guard can come see us. Right? Now we've got this and we're holding it up there and whatever. Right? Okay. So this is Morse code, right? Now, great. We've actually done this so that it's interesting though. Like, do we still, computers have how many numbers, really? 2. A 0 and a 1, right? 2 symbols, if you will. How many symbols are we using in this? 2 as well. But they're weirdly asymmetrical though, right? You've got the symbol like the dot, which is a 1 length in time, and then a dash, which is a 3 length in time. It seems a bit odd. Now it's nice if you're sending Morse code over a wire that you can, if you're listening to this and whatever, you can do that. But the thing is, we want to be able to do this like faster, and we want to be able to do it using just the symbols that we kind of already know, like how about 1s and 0s are really voltage on, voltage off. That's kind of what we want to do, right? Now, that said, there are automatic ways of sending Morse. In fact, when I was in the Navy, I was a cryptologist in the Navy, and we sailed around the world, and I literally had a guy on my staff who knew Morse code, and he would have headphones on, and he'd go around, and we'd be like near the Philippines or something, and he'd be listening to Morse code, just copying it down. Like, that was what it was. Now, why we didn't figure out how to just record it and manually or automatically do that, that's the Navy for you. But anyway, people literally around the world are still sending Morse code, which seems odd. And then, of course, there's ham operators and amateur radio operators who use this all the time as well. But the point is that we kind of want to make it, we want to make it so that it's a little easier to do automatically, so we can speed this whole thing up and use the types of characters that we already know, the types of symbols we already know, which are 0s and 1s. Okay, so how might we do that? Well, in the late 1800s, there was a guy named Baudot who came up with a 5-character code, okay, or basically 5-symbol code that was similar in principle to Morse, except that now it just said, look, we're going to just have 5 symbols down here. The little line in the middle is just so you can align this paper tape when they're like reading it in. And those, you'd have 2 symbols up here and then 3 down here, and that would make up a character. So A in this case would be 2 like holes in the paper tape, and then no holes down here would be A, right? And then B would be a hole here, no hole, or no hole, and 2 holes down there, etc. In fact, this is not the original Baudot code. This is actually the kind of the first version that they used for teletype. The cool thing about the original version, let me actually show it to you. The original version here is, where is it here? Baudot code, there we go. Oh, nope, this one. Okay, let me break this up a little bigger. It's actually called a gray code, which means that subsequent letters are actually 1 bit apart, if you will. So it turns out they had the little E with the accent on there as well. But if you look, the difference between A and E is a single bit difference, and then the difference between E with the accent and then E is another 1 bit difference, then 1 bit, and then notice that? That's actually kind of nice for error correcting, as it turns out, and some other reasons that it made it easier when they were trying to like debug it and so forth, and also just do some error correcting. So that's the original Baudot code. But the point is that they could feed this through at a certain rate, and that rate, the number of symbols per second, and each one of these is like a symbol. The number of symbols per second has been and is called the baud rate, and it's named after this Baudot code. So if you ever heard of baud rate, like 9600 baud, right? You guys old enough to remember 56K modems? You guys probably aren't. Nobody even has any idea. Okay, does this? Nobody's any. Boy, that makes me feel old here. Does this sound like anything to anybody? Hold on. You guys are like, I've never heard that in my life. I know, Phil's back here going, oh my God, I can't believe it. Okay, that is the sound of a modem connecting to another modem and trying to figure out what baud rate it can actually go on. And it keeps doing this, and there's a bang. Everybody who knows this, there it goes. And then it finally connects. So that was what people of my generation used to think of when we thought about like computers communicating, is that noise, like the modem connecting noise. But the idea is that 9600 baud means 9600 symbols per second. A lot of times we end up doing bits per second because we can end up transferring 1 bit per second as we go along. Okay, I think the coolest thing when I was looking up Baudot codes on here is that the original like human version of doing this, in fact, I don't think it ever made it into teletypes. The original human version of this was they had piano keys. Like literally, they retool the piano and make piano keys, and like you would sit there, you'd put 3 fingers over here and 2 fingers over here, and then you'd learn how to do these codes pretty fast, and it would put them onto the paper tape that would then get read and so forth. So kind of neat when they came up with this. Okay, so today, the Baudot codes have kind of been modified over the years to be a little more standardized, and today we use what we call ASCII. Okay, who's heard of ASCII at this point? Yeah, actually, if you did anything, if you did 106B, you would have used it for some of those things. But ASCII is the code that's used to have the letters, the numbers, the digits. Codes numbers 0 through 127 are actually ASCII codes. This chart is nice and compact. It's a little weird to read. If you want like lowercase c, you go over to the 6 and then down to the c and you go, okay, 6-3. So you look at the c and you go, it's 6-3, and that's the hexadecimal value for c. Okay, and that's how you read this. I think it's a little easier actually if you do if you go to your terminal and just type man ASCII and then pay no attention to. Let me get this a little smaller so that. There we go. Pay no attention to the first one in the Mac because it's the octal set, which is we're almost never going to use. But the next one's a hexadecimal one, and this one just lays it out a little bit. So if we go down to C, we'll notice, oh, it's 63. Okay, so you can look these up if you need to. Go look up your ASCII codes just by typing man ASCII at the terminal, man ASCII, and that will do it, and you can actually look all those up if you need to. Okay? This code is the one that, like I said, it's been quantified over the years. IBM had its own version of a character code, and somebody just made this up, by the way. One of the nice things about this code is that it turns out that they purposely did this so that uppercase letters and lowercase letters are only off by 1 bit, the 5th bit over, I believe it is. So that's kind of nice. You can easily transfer, you can easily convert lowercase to uppercase or and so forth. And this was all back in the day where we were limited in the amount of characters we could send anyway, and so that made a difference. But the ASCII code is the one that we use today, and it's the one that we're going to concentrate on when we're talking about all of these ones and zeros for how to send a signal. And again, somebody made this up, right? It was a committee that made up the ASCII code, and they purposely did it in various specific ways. And it's just a human invention. There's nothing special about lowercase c being 6-3, or 6-3. It just happens that they made this up, and that's the way it goes. Okay, so that's the ASCII code. Okay. Now, when we're actually doing communications, okay, well, now is where we get to the idea of, oh, now that I have a code that is quantified as ones and zeros, can't I just send a bunch of ones and zeros across some wire? And it's different than Morse, because Morse, remember, used the dot and the dash. They were both like high symbols. Okay, like in other words, they were both like, oh, the voltage is high for both a dot and a dash. Now we're saying ones are going to be a high voltage, zeros are going to be a low voltage, and we are going to quantify this. Now, there are many, many different standards for how to do this. We have kind of landed on one in particular called the asynchronous serial communication. It looks like this. It starts, okay, first of all, the line generally stays high normally. Okay, so in other words, if nothing is being sent on this medium that we're transferring across a wire, the line is 5 volts. Okay, so if nothing's happening, it's just a straight up 5 volts. Then it starts with what we call a start bit, which means you're going to go low for the amount of time that we've decided our baud rate is going to be. You're going to go low for that amount of time, and then you're going to start the character. And if you're doing the ASCII character, here's how it goes. 8 bits, 1, 2, 3, 4, 5, 6, 7, 8. Notice something interesting about this. It starts with the least significant bit. It seems a little odd again, but that's the way this communication, that's the way the people who designed it came up with it. They said, oh, it's going to start with the least significant bit, and we'll do that. So if we look at that, like, what does that actually mean in terms of least significant bit? What did we say lowercase c was? It was 6-3, right? Let's do it right down here. It was 6-3. Okay, what's the hex for 6? Or sorry, the binary for 6 if we're doing hexadecimal?
110.
How about 0, 1, 1, 0, and then the 3? 0, 0, 1, 1. This would get sent like this. You would get if you're doing this communications protocol, you would send a 0 to start. That's the start bit. Start bit. Whoops, bit. Okay. Then you would send a 1, 1, 0, 0, because we start and we go this way. That's how it's going to do it. Okay, so it's going to be 1, 1, 0, 0, and then 0, 1, 1, 0. And then it's going to do a stop bit, which is going to be a 1, and then it's just going to continue as a 1. Yeah, question, John?
So the start bit's always 0, but say I'm trying to send 62.
Yeah.
That's least significant bit is
Yep.
0.
Yeah, so this is all timed. Okay, we know how frequently. There are other codes, by the way, which don't rely on precise timing. This is not one of them. This code relies on being able to say, okay, if you see the line go low, right? And then the reason there's a start bit is so you have some time to figure that out, right? You're like listening, oh, I got some time, and maybe you'll miss a little bit of that start, but it's enough time to go, okay, great. Now I'm going to start the process of jumping to my function. It's going to start reading the bits, right? It's going to get the low bit, and then it's going to go, okay, this is the start one. And if it happened to be a 0, fine. It's just another 0, but we know that the time starts there for the first bit. All about timing in this case. Good question. Okay. All right. See how that works? Everybody kind of get the idea there? Okay. What other questions do you have about that at this point? Good. Okay. So again, by the way, if we're trying to do 9,600 bits per second, that's zeros and ones per second, right? That is actually 104 microseconds for each bit. Doesn't seem like much time. It's not that much time. We can do a lot better than that. In fact, this 9600 baud is relatively slow. In fact, the ones you're going to be using for class or for your assignments are going to be 115 200. That's how many. That's the baud that we're going to use for most of the ones we look at. Okay. All right. So now we're going to do a little bit more. Now we're going to actually go and write a little serial one to flash our light in the way that we want it to, right? On and off like this. Okay, so let's actually go and do this. Now we're going to go to, let's see, what is it? What did I say? It's going to be, it's going to be serial. Okay. Oops, not. How about serial.c? There we go. Okay. What we're going to do is we're going to write some functions that are going to do exactly what we just said, and we're going to do it in the protocol that we just learned about. Okay. So here's what I've got. I've got the baud. We're going to set to 9600 baud. Okay. And we're going to have the delay be 1 million divided by the baud rate, which is how much we're going to delay, because remember we just wanted that delay per second, as it turns out. Okay. It's a similar sort of thing for, we're going to decompose this into a couple different things, like to send a bit, what do we need to do to make the light be a bit? A 1 bit, we should say, or a 0 bit, depending on which it is. What do we have to do? We have to take our output pin 20 and do what? Write to it, all right? So we do there we go, GPIO, right, and now we have to pin, and now we have the value that we want, which is what we're going to get passed in when we do that. And then we have to do what? To keep the light on for some amount of time, right? Timer, delay, milliseconds by our delay, which we just came up with. Okay, that's it. Okay. Now we're going to write a little function called putchar, which basically we want to put the entire character that we just did in this form that we said. Okay, let's remind ourselves what the form was. Okay, we have a start bit, the 8 bits going from lowest significant bit to most significant, the least significant bit to most significant bit, and then we have a 1 as a stop bit. All right, so what do we need to do first? First thing we need to do up there, start bit, which means we just wrote a function called bit. So let's do that. What is this value of start bit? 0, bit 0. Okay, that's our start bit. Okay, and then we need to, do the output of 8 bits, least significant bit first. Okay, how are we going to do this? Any idea? How are we going to print it? Yeah, go ahead.
We mask with the first bit.
Yeah, we're going to mask out the first bit. That's probably the easiest way to do it, right? There's different other ways you could do that, but let's actually do that. So we're going to mask out the first bit, but can we do this? We're going to do all of them, right? So how about a for loop, right? How about for int I equals 0, I is less than 8, I plus plus, because we're going to do all of the bits in there. Okay, and then we are going to mask out the first one. How are we going to do that? We're going to call bit, and then we're going to put in there masking out the first one. What's the way we mask out the lowest significant bit? What is it? Mod 2. Interesting idea. I think that would probably work. Let's do it using our bit operation instead of a mod operation. Yeah, go ahead.
And with 1.
Yeah, and with 1. How about that? And it with 0x1. That would work. It would, by the way, the compiler would have turned that into an and 1. Would have done that. Yeah.
Is 0x1, could you just do decimal 1 too?
You could just do 1.
Okay.
Yeah, either way. I like to do 0x1 because it's kind of a little more standard when you're doing masking in that case. We could also have done 0b1 if you wanted to. Same sort of thing. But in this case, 0x1. 1 is 1 in pretty much every base, right, as it turns out. Okay, so we're going to do that, and then what do we have to do to our number? Right shift by how much? 1. How about, we'll do it that way. There we go. And that will do it all. Okay, so then we've printed out our bits, and then what's the last thing we need to do? Stop bit, and what did we say the stop bit was? A 1, so let's do the same thing. So a bit, how about a bit of 1? There's our stop bit. And then what do we have to do after the end of our character generally? This one I didn't tell you about, but this is basically saying you're going to need some time between words, or letters I should say. You need some time to do that. So we're going to do another delay. In this case, let's just do it delay microsecond, 2 times the delay. You could play around with this, but that's going to be what the standard is going to generally be looking for. Now it doesn't really matter, as it? Well, it doesn't matter. This is for one character at a time to do this. Okay, you have to have some delay. We're just going to pick that in there. Okay, let's do a whole string, kind of like what we did before. This one's actually even easier. Which function are we going to use now that we have our put string? put char, right? We're gonna do the same thing, right? But we're gonna go through all the characters. Watch this. While star s put char star s plus plus semicolon. That's it. A nice easy function there. Let's parse this out. Okay, we're going through while the pointer to the string is not null. And remember, strings are null terminated. So if we pass in a legitimate string, this will work fine. Okay, and then it puts the current character, then updates the pointer to s, and then repeats until it becomes null. Yeah.
If you know that each character is like 8 bits, why do we need to like stop and start?
If we know that, okay, again, that's a good question. If we know that if each character is 8 bits, why do we have to do the start and stop? The start bit is basically to say, okay, I'm listening to this high line. It's going to go low. Let's give it time. Let's know that that's when we start, and then go. It's basically kind of it's basically a timing issue in that case. Yeah. Okay. It makes it a little easier to time the whole thing electronically, as it turns out. Phil?
Also, clocks are never equal. And so
Yeah, this is another.
one side is basically saying, hey, we're going to sample at the same speed. If your clock is off by a couple parts per range, they always are. If you just send streams of bits, eventually they'll be synchronized and they're not sampled at the right rate. So basically, a serial port just sends a single 8 bits. You only need to remain synchronized. You have to be synchronized well enough to stay on those 8 bits. And then you start again. You resynchronize on this stuff.
Yeah, this is a very good question. So.
This will come up later when we do the other buses.
Yeah, when we do it, you're definitely going to want to be able to synchronize, and that's kind of the handshaking thing that goes along there. When you say you're looking for, if you've got all off and you started getting more bits than you thought, well then you kind of resync eventually by knowing that this start bit and stop bit are there. It's a good point, and I'm going to demonstrate that in a little bit too. Yeah.
When you're doing like the pointer s plus plus,
Mm-hmm.
so that's pointer like moving the pointer
Oops.
forward, but why wouldn't that be like incrementing the dereferenced value?
Yeah. Turns out that this is how you read this. You say, okay, fine. The plus plus is going to happen after I read the value, right? And then so you're going to read the value, and then you're going to update. You're going to do plus plus. Turns out plus plus binds to the pointer itself, not to the actual value of the pointer. Binds a little tighter than that. I know. Phil's going, this is crazy. You should put parentheses. The reason I do this stuff, now you could rewrite this in many different ways to make it more clear. Unfortunately, you'll see a lot of C code that looks exactly like this, so you better get used to it if you don't end up doing it yourself. Yeah.
Yeah, I don't think it's good, but it's just the grammar. It's the way it works.
It's the grammar,
Why
yeah.
is it that like an adjective in English like binds to the word that's after it, right? With the word that's before it. It's just the rules. And eventually, as you read this, like any language, you just naturally then know what the precedence is, and you know what the expression is. It just takes a little bit of practice.
And look, you can go test it too. And actually this week we're going to show you how to use the debugger, so you can go test it and actually print out values and see what these things are too as you go along. Okay, so and then in this case what we're going to do is we're going to, now that I've done that, I can show you the main function, which is basically, again, do the timer, set up the GPIO pin, set the pin 20 to be output, and then it's just going to do this. It's going to go, hello laptop, hello laptop, hello laptop, hello laptop, etc., etc. Okay. Now, when we do this, if we do make install, I have to do this again. Okay. How fast did we say this is going? 9600 baud. So if I do this, then there we go. Okay. Oop, this isn't the one. Hang on. Is that the one? Oh, that is the one. What can we read that fast? There's a lot going on there, right? There's a lot happening there. Let's actually do this with a little more technology. Okay? What I have is a program here that, actually I'll make this a little bit bigger. Okay, what it does is it reads values. If I connect up it's called a logic analyzer, and what it does is it reads the values off of pins as it runs, and you can collect what we call samples off this. Okay, let's see if this actually works here. Oops. We are going to collect a bunch of samples here. Let's see, I think that should do it. There we go. So it's collecting at 500 kilohertz. That's 500,000 samples per second, and it just collected 1 million samples like that, right? And hopefully I've got everything. Oh, you know what? I don't think I have it set up right now. Hold on. I need to plug this into the proper location, which is not that one because I put the new, yeah, there we go. What I'm going to do is I'm going to measure it from the actual LED itself. So hopefully that one should do it. There we go. Let's try this again. Run. Okay, it's collecting, collecting, collecting. There we go. Okay, so you can notice in there that it's collecting a whole bunch of samples. Let's actually do this. Let's actually make it collect more samples. And it still doesn't, you know what? I don't think this is running the right program. Hold on. The reason I say that is because, let's see. Delay in there. I just don't think it's running the right thing. Hang on. Let's try this. That. Oops. Of course it's not doing that. There we go. No, same. Okay, hold on. Let's actually do this again. We'll collect more samples here. Okay. All right. So let's actually do this and take a look at this. I'm not sure why it's not. This should be running a little faster, I think, and I'm not sure what's going on with that there. Yeah, hold on. Let's do serial.c. Yeah, let's see if we can find the bug. Yeah.
We have our timer delay function is in milliseconds, but your delay is coded for microseconds. Like you've got a million over baud.
I've got 1,000,000 divided by baud. That should be the right one, though.
Line 12. Line 12.
Yep, there you go. Yeah. What should we be doing here on this line for our bit? It should be timer delay microseconds. Very good. All right, should all of them, are there any others in here that are microseconds? Let's see, that one is, and the one down here is also micro. That one we got right. And then the one down here is also, there we go. Whew, I knew that didn't look right. Like something's weird about that. Let's try this again. Thanks for helping me debug that. Okay. All right. There we go. That's what I was expecting. I wonder why I was looking so slow before. Okay, can you tell that's blinking? You cannot, right? Before we could. Let's do this again. Let's try collecting samples now and see what, this looks a little better. Now we've got lots and lots and lots and lots of samples in there, okay? And can you tell where the various things are? What's happening here? It's a nice long delay there. What's happening there? That's where the beginning of the, that's where the high line is. In other words, it's waiting to read a character. And then it goes, there's a start bit in here, and then some zeros in here, and then a 1 and a 0, and some more zeros, etc. Right? Now, we could decode this if we wanted to. We could go and we could look, and we could say, okay, well, look, there's a start bit of 0, and there's got to be a 0, and a 0, and a 0, and a 1, 0, etc., like we did before. Or we could know that the people who built this have the ability, oops, that was not the right one, hang on. They set it up so that we can read what we call the UART, which is the one we're going to look at in a few minutes here. And if we do this, and this was at 9600 baud, okay, and it was pin 0 as it goes on there. And let's do it in ASCII. Ta-da! Look at that. H-E-L, hang on there, hang on, it went too big, there we go. There we go. Here, we'll start over here. There we go. H 0 0 0 1 0 1 1 0. But you read it backwards, right? You go 0 1 1 0 1 1 0 0 0. That's H. And then there's a start bit and a stop bit in there. And then same thing. And then this is an E. And then L, etc. And it goes all the way over. And keep going, keep going, keep going. And then hello, comma, and then a space. And then hello laptop, and you end up with, these are interesting characters here, 0A and 0D. We know what that is? It's the end of the string. It's the new line that's going to happen on there. Yeah. Pretty cool, huh? That actually worked. And you can actually look at it in here using this logic analyzer. We do have a logic analyzer in the lab too, I believe. So if you guys, we have a couple. If you want to plug your pies up to this, you can actually do it. It's different software than this though. This is the one that we have in the lab. Okay, so that's how we just did it. This is the logic analyzer that we just looked at. Okay, questions on that at this point? Notice that we've now gone from Morse code to like ones and zeros being our code. We've quantified it so that we can actually talk between two things. Right now we've just got this light blinking faster than we can see. Okay, but we can use the tools to actually do that. Question?
Since the high signal is the default, if it cuts to low, like if the wire gets cut or something happens, how long does it take you to realize you don't just need a bunch of zeros?
That's a good question. Well, remember there would be no stop bit. So it would maybe read a bunch of zeros and go, oh, it looked like a bunch of zeros. And then it'd go, where's my stop bit? And it would have no idea where to, like, because the stop bit is high again, right? So it would have to catch, whenever it started, like, it would have some timeout delay in there and then start picking it up at some point. Depends on the system you're looking at. Phil, do you have anything more to add to that? I think that's pretty much it. Who else had their hand up? Anybody else? Yeah.
Is there any rule for the idle time?
Is there any rule? Yeah. So this is you can cut it pretty close, I think, but I think the like 2 times delay character width is probably about what you want. You want to have it at least 1 character in there so that you can see the stop bit, see a little bit extra time, probably 2 stop bits, and then see a start bit again. Yeah. Okay. Now it turns out, by the way, that this is a nice enough like system that we can actually, let's do this. Let's fool around with it a bit. Let's say instead of 9600, let's make it 9650. What do you think? Whoops, I don't want to do it. There we go. Okay. If we do 9650, let's see. Let's do it again. Let's install it. And installed. Okay. Looks about the same. Okay, let's collect some more data on this again. Okay, it's collecting right now. Okay, well look at this. And then the timing is going to be off on this though, but take a look. It was fine, right? It ended up, you can be off by a little bit and it won't actually, it can still catch up. Now, if you did it long enough, yeah, maybe it would get out of sync enough that it would have to catch up. But the fact is that the reason there's this, a wide enough gap is that it's not just reading right at the beginning. It's kind of saying, okay, I'm reading at the beginning and it could either actually take the measurement a little later on, or it could, it's all about timing, and the timing can still be a little bit off base and still give you a proper reading. So that's kind of nice. As Phil said, sometimes clocks are different. In fact, they're always a little bit different. Your clock might be different than the one on the other end of the signal listening, and that's the way it goes. We haven't even gotten into the fact that how things actually listen yet. We will. Okay. All right. Now, so the little device that you guys have, let me see if I have, there we go. You guys have one of these connected to your Pies right now, right? And you've been using that as your bootloader to like load programs on. We can also use it as a communication between your laptop and the Pi. I mean, that's what the bootloader is doing. But we can do it for anything we want. And we can actually quantify this and then actually look at it. Okay, so what we're going to do is we're going to do this, and in fact, you can use a program called Screen to actually look at the data that's coming back. So in fact, if we go down here and we say Screen, and then slash /tt dev/tty, and mine is actually a little bit different. It's actually C. It's a little different than the ones you might see. Hang on. cu.usb serial A9M9DV3R, and then 9600. Oh no, did it not connect? I don't know if it's connected. Hang on. Dev tty. Oh, it's not /tty. It's dot. Sorry, dot. See. Oh no. Nope. tty.c. Nope, not in there. Hang on. Let's see. There it is. tty USB serial. There we go. Okay. And if I do screen of that, and 9600. Not connected right now, but hang on, it must be not connected to the right pin. We want the receive, which I believe is this one. Hold on. This, if I put that also on the same pin there. Nope, not working. I'll have to I must have the wrong one. That one is, maybe it's the other one. Hold on. How about this one? Yeah, let's try this one. Nope, still not receiving. Hang on. I'm basically just trying to figure out which pin is supposedly connected to the Pi for the receiving. Nope. Hang on. Last chance, and then we'll go on and move on to that. Nope, still not collecting. It must not be collecting right now. But the idea is that you can use the screen program to actually see what's actually coming over the line as well, and I will show you an example of that in a minute. Okay, and you'll be doing this in lab as you go along as well. Okay, so you're going to connect this up. Remember how we connected the transfer on the USB serial device to the receive on the Pi, and then the other way around for the Pi to the receive. You can actually do it this way. If you want to test your serial port, just connect the receive to the transmit and the transmit to the receive on the actual one itself, and you can actually test it out as you go. Okay, I want to show you another program that we're going to look at called the UART program. Okay, UART is actually now using the serial communications on here. Before I show you the program, let me just show you a couple other things about this. Remember our GPL, we had 54 pins, and people have been asking about what are all the other alternate functions and things? Well, one of the alternate functions for pins 14 and 15, 14 alternate 0 is the transfer. So it's going to know to use this protocol we had that we talked about to do this. And then 15, the alt 0 is to receive as well. So when you set those up, the actual processor will go, oh, you want to communicate using this start bit, stop bit business? Great, we'll do it that way. Okay, so it does it for you, so you don't have to actually do all those details. Okay, so those are the ones we've already been connected up to. And like I said, I'm not sure why it's not showing me this there. If you look at the actual UART itself, there's a lot of details here. There's a lot of things going on. You've got this big struct that has all these interesting details in here that we don't need to know about quite yet. This one will become interesting, become interesting a little bit later on in the course. So we'll see about that. But it's got things like, it's got something that tells you how fast it is, it's got some other status things, it's got some control, so it's got some other details kind of built into that. The UART is kind of the expanded version of this very simple code that we talked about in terms of lots of other details to make it work in various situations. Okay, so let's actually look at this. Hopefully I'll be able to get this one to work here. Echo. Okay, so in this case, if we look at the echo file, here's what we're going to do. We're going to have this, actually I'll show you the UART, I'll show you UART as well. But echo is basically going to do this. It's going to get a character from the Pi, and then it is, it is going to get a character from the Pi, and then it's going to send it back to the Pi as well. So it's going to be what we call an echo. If I type an A, it's going to send an A, and then it's going to receive an A. And it's actually the other way around. It's going to receive an A and then send. Phil, you have a question about that? No, okay. And so that's what we're going to basically do with this little echo function here. Okay. Let me see UART here for a sec. Okay. UART.c. In here, you've got all this. This is that struct we were talking about, and then a whole bunch of auxiliary things. These are things that we're not. I don't think we're going to make you like stress out about this UART thing, but it basically is quantifying all of this details. And you can go look at the code here to tell you how fast, to tell you exactly what's going on. And it's actually not that much code here to worry about, right? Put char is going to basically, it's going to put the data onto the into the transfer, and then getChar is going to read it off. Okay, so that's what's going on there. Let's see. We want to do echo. Okay. All right. Now here's what I want to do. I want to do this, and so it's not going to work because I need to reset the pi. Okay, so this actually supposedly is connected upright, but this might be a case where my wiring is wrong, or somehow came out when I walked downstairs. Let me see if we can do this real quick. Let's see. This one, this one, this one. And yes, here it is. Nope, that's not it. And then let's see. Ooh, hold on. That doesn't look good. Okay, let's try this again. Yeah, I know. You're like, whoa, what's going on? There's garbage in there. Okay. Let's try it again, see if it works. Nope. Best laid plans. Come on, one more time. There we go. Nope. Let me try it again. Nope. Okay, hold on. Let's take this out here, and we'll see if maybe it's... Okay, hold on. Reset the whole thing and try it again. And, oh, what's this one? Hold on. That is the transfer, which is supposed to be, which pin did we say it was? How about that? Okay, try that. Hold on. Okay, make install. Do it, please. Thank you. Okay, there we go. So now I'm typing up here, and it's actually, I'm typing, it's sending to the Pi. And if you look on my little device, you can't see that from here, but if you look on my device, as I type, it actually has the little lights blink for the transfer and receive on my device here. Let's actually do this. If I plug this into, if I plug the logic analyzer in here, what did we say the baud rate was here? 115, I think. Let's actually try this. If I run it, let's do that. We'll do that. Let's do 5 million samples. Try a bunch of samples here. Okay. If I run it now and I go over here and I type A, B, C, D, E, F, G, okay, and it's still collecting. There we go. Take a look. Here's my not so quick typing here. What should that be? Frame error. Great. Oh, I know why. Why is it a frame error? What did we say that the baud rate was, right? 115,200. Ta-da! There we go. There's my A, right? And if you look farther over, then somewhere over here, because I can't type that fast. Notice, by the way, you can measure the time on these things. If you look at this, the amount of time between characters for me, like I typed an A, then a B, 68 milliseconds between characters. Right? The computer can do millions and millions and millions of things while I'm like my fingers going up and back down again. Right? That's how fast these things are compared to that. But if we look at that first one was an A, this next one should be a B, etc. Okay? So that is that's how we use the thing. And by the way, if you're in this screen program, you have to hit Control A and then K, and it asks you if you want to kill the window, and you do. So it's like that. But again, let's look at the program here. This is all it is to do this, which is kind of nice because you guys are going to write some functions that are going to use the UART to send data back and forth from your Pi. Okay, this one's just one character at a time. Okay, we can also, if we look at, let's see, serial. I think that might be, hang on, that might be next here. There we go. We'll get to that in a second. If we look at serial here, remember, we sent hello laptop using, or before we sent hello laptop using the write commands, but couldn't we just do the exact same thing instead of using the writing to a LED, just outputting to with a UART to the actual Pi? So then we can communicate back and forth to the Pi like that. Let's see, I think UART actually has a make install that does this for us. Okay, let's try this. And there we go. And now it's going to do the same sort of thing. Now it's actually sending, we're receiving from the Pi, hello laptop. And if we go and do the collecting here, then it should collect for a little while if I connect to the right pin. Hopefully I connect to the right pin this time. There we go. Same sort of thing. And what's going to happen down here, we get hello laptop again. And now it's actually receiving the characters hello laptop from the Pi, and that's how it works. It's pretty cool. Okay, screen is actually receiving that here. So it's just sending it, and it will send it forever and ever more. And just keep sending it like that. Okay, last thing we're going to talk about here. Good, we actually have plenty of time. So I mentioned C strings. Okay? Strings in C are very, very simple in principle. They are a bunch of characters followed by a null. That's it. They don't know their own length. They don't know, you can't add to a string. There's no appending to a string and whatever. You can have a string that's all it really is an array of characters. And it's an array of characters or a pointer to a memory location which has a bunch of characters followed by a 0. That's the whole business with strings. Okay? So you can start out like this. Turns out we found out, Matthew, correct me if I'm wrong, we found out about you can't initialize arrays like this in your code yet?
Yeah, array.
Yeah, it ends up, if you try to do this in your code, you'll end up getting an error about memcopy, as it turns out. So you kind of got to do it a little bit differently. You have to like manually populate it. But if we wanted to, that's one way to do a char array that says CS107e with the little null character on the end. \0 just means the character 0, not the character 0 that was like 1, 0, 1, 2, 3. It means the ASCII value of 0. Okay, and you could also say, instead you could say char array equals, and then this will put the little null terminator on it for you if you want to do that. It's a slightly different way of doing that. You could also say this, char asterisk pointer equals this, because this is now going to be a pointer to that character string as well. Yeah?
Which one of these can't you use without
You-
memcopy?
You can't, the first two you can't, I'm not sure about the second one, but I think at least the first one you're not going to be able to do it that way. You can try it with both, but if you get the error message, go, oh, there's got to be a different way to do it. We've got to do it in a different way. Okay. All right. So can we do this? Can we say ch equals ARR1 if we had AR like this? Sure. Why not? Right? It turns out you can use array notation for an array like this, and it will get you the char array. What's it going to be in this case? ARR bracket 1. S in this case, because CS, right? Same thing here, okay? Array equals pointer. This is not going to be allowed, okay? So if you look at this, this right here is not allowed. Why? Because you can't set the value of an array because it's not a pointer. So you're not going to be able to do that. That would give you an error, okay? Pointer equals array. You could do this. You could reset the value of a pointer to an array because this array gives you back the value of the memory location that it's pointing at. Okay? What does this mean again? Char star star? It's a pointer to a pointer. Okay, that's what it says here, right? Pointer to pointer. It's a pointer to a char pointer in this case, right? So it's going to be the address stored in PTR is going to be an address of a pointer to a char, not an address to an actual char itself. Okay? So let's actually draw this out since we have time here. Let's actually draw this out like this. Let's do this. Let's say that we have this, and sorry, my drawing is going to be kind of terrible here. Okay, and I'll just do a few of the letters in here so that we know how to do this. Okay, let's say that we had. Let's use. Let's see. We're going to do. Let's do both here. We'll do array is going to live up here. Let's say array lives up here. Let's call this location, I don't know, 20. Okay, this is the address 20. I'll do it this way. I'll just say A20 for an address. This is address 20. Okay, and if we did this top one here, it would be C. What address is this going to be? The one next one up. 21. Yep, because they're characters. CS1, etc. Okay, that's what that's going to be. Okay, if we then say char asterisk pointer equals CS107, then we have a value. Let's say we've got pointer down here, which is, let's say that's at location, let's say that's at location 10. Well, we should probably do this correctly. 19, 18, 17. This will be at location 16. Okay, let's say that pointer, we do that, and let's say that this character string starts, let's just say it starts here. I know it's going to overlap. But let's just say it starts here. C, S, and then dot, dot, dot. Okay? Pointer equals CS107e. What location is going to be held in PTR? 18, right? Because it is a pointer to a character. Okay, so this points up to here like that. So far, so good? Okay, then we've got, remember, this is not going to actually work. This one would work, and then that would now, what would happen if we did this? What would pointer change to? 20. This would now be 20. Okay, 20. And the pointer here is now going to point up to here, like that. Okay, and then now we have char star star PTR PTR. Well, that means we're going to create somewhere else. Let's just do it down a little ways here. Okay. Okay. By the way, we've also got a problem here because how much space does PTR take up here? 4 bytes, right? So it would overlap there. So my diagram's terrible here. But this would take up 4 bytes. So same thing down here. I'll do this. I'll make it this one actually work here. I'll say this is going to be PTR, PTR. Let's say this was at location 12, 12, 13, 14, 15, 16. There we go. Okay, 12. Okay, at the moment it's got garbage in it when we do this because it's not, we haven't set it equal to anything yet, but it has space for it. And then if I do PTR, PTR equals ampersand ARR. That one is a little weird. It actually gives us the location of what? It gives us the memory address what? Does this even work? It would kind of work, but you'd get a warning, I believe, in this case, because it would give you a pointer to a char, not a pointer to a char. So we don't like this way of doing this either. This one, on the other hand, what value is going to be in PTR, PTR? If I do PTR, PTR equals ampersand PTR, 16. So now this is going to point here, and you've got a pointer to a pointer. Does that make sense how these work? You're gonna have to practice a little bit of this, writing some of these things out. You'll do some of this in lab, and you'll also do some of it in the next assignment. Questions on this before I erase the diagram? Okay, erasing diagram. Okay. There are lots of string functions in string.h. You guys are going to write most of them. All right? You guys are going to write most of them. You're going to write, they're not really that hard to write. You have to be a little bit careful about them, and you have to know exactly the way that they work. So for instance, stir copy S1, S2. Well, believe it or not, this is the source, and this is the destination. Right? So it copies the source into the destination. And when you're writing this, you got to know, oh, that's how it works. Okay, where do you find all this stuff out, by the way? Well, you can look on this chart here. Or you can also just do, so for instance, you can do man stir copy. Right? And it says, oh, okay, here's how stir copy works. Okay, stir copy says, I've got a, where is it here? Stir copy, I've got a source going to a destination. See how that works? You can look these up like this, and then it will say other various details about it too, like it will say what the return value is. So the stir copy actually returns the destination, like what it returns the pointer you sent to it to begin with. That seems a little odd, but it does that. Yeah, question.
Should we worry about like memory leaks or like losing data?
Oh, you should worry about memory leaks. We haven't talked about that quite yet, though. Yes, you should worry about that, but think about what you have to do first. Then we'll talk about memory leaks and how that actually happens here. Okay? Take a look at this. Here's stir length. Remember how strings don't know their own length? You actually have to calculate the length. Okay? So what are we doing here? We are saying, okay, a weird for loop like this. Okay, it says constant char s asterisk s equals string, the str that we pass in, and then it's basically while that is not a null value, increment it, and then do nothing. Right? What's that actually doing? What's it doing to str in this case? We should talk about it if that's not quite clear. It is a little bit weird. John, you have a question?
Why is it plus plus S now instead of S?
Oh yeah, what's the difference between plus plus s and s plus plus?
Does the operation first.
Yeah, it does the operation, does the plus plus before it does that. In this case, it's irrelevant because of the way this actually works. It doesn't actually matter. But in this case, it says, oh, before I do anything with that value, I'm going to increment it first. That's the difference. You're going to answer what it was doing here?
Yeah, so
Yeah.
it says S to the furthest over.
Yeah, it sets s to the first value. Oh, okay, so we have, let's go back up here. We have the string in here, str. Okay, let's say that str points down to here. Okay, and it's A, B, C, and then a new line, or sorry, a null character like this. It was A, B, C, and then that. Let's say that's what our string looked like, right? What this does is it creates another variable called s, right, which starts out pointing here, and then it goes until s is not equal to null, and it just does what? It increments it. So it goes, okay, it goes until the value at that, it goes until the value there is not equal to null. And it increments it, so it goes there, then it goes here, then it goes here, then it goes here, and that's how it figures it out. Let's put some numbers in here. Let's say this was location 20, 21, 22, 20, 23. Okay, and then what does it do? It returns s minus stir. S is what value? 20. Sorry, s is 23. What's the value of stir? 23 minus 20 is 3. Is that the length of the string A, B, C? It is. This actually works. It's weird, but it works pretty well. Yeah, Elise.
Do you need ampersands?
You don't need any ampersands.
Why not?
Why would you?
Because if you're subtracting the memory address of stir, like if you're using s and then subtracting, but both of those are memory addresses, right?
This is a memory address, S, right? So it's already a memory address. And it's, in this case, it was value 20. Let's say it was pointing at, if it was pointing at this A and this A lived at value 20, then S has the value 20, S has the value 23 in this case.
So if you said
Right.
ampersand s, would that be the null?
Ampersand S would be weird. It'd be wherever this location is. They don't want that, right? You want the value of S, which by the time it gets up here is 23.
Right.
The value of S. Question.
How come S wouldn't fall out of scope?
How come S wouldn't fall out of
It's like declared inside the for loop.
scope? Oh, you know what? It would, wouldn't it? I think you would probably have to do that up here. That's a good point. I don't know why it's like this. It should be const char star s equals stir up there. Or just define it like that and then say it. That's a good point. Yeah, thanks. Yeah.
So characters are 8 bits, right? So when you do s minus string, it's not actually returning the difference in memory addresses, but divided that difference divided by 8.
Okay, remember, addresses are 8 bytes each. So this is an 8 byte, 8 byte, 8 byte, 8 byte, right? So there is no memory addressing of any individual bits.
Right.
So it's just this is this address minus this address for 3, because there's 3 characters in that string. It doesn't count the okay. Does that make sense? I think you're overthinking it a little bit. Jean-Luc?
Each address is 8 bits.
And each address refers to an 8-bit location. Yes.
Why'd you make it constant?
Yeah. So this is just basically saying when you say const char asterisk s, it means I am not going to change the values that points to. In other words, I'm not changing the string. That's what that means. It doesn't mean that s can't change. S itself can change, but the characters that s points to can't change.
If we didn't include that, well,
If you didn't include that, it would work just fine. But it's a little safer this way, knowing that that's the case, because then you know you can't accidentally set it if you somehow in there set it. If you want to. Yeah.
What size T?
Good question. Is size T. Size T actually refers to it's basically a number that can hold a number as big as any length on the computer. Basically, it basically says if you filled up all your memory, all 32 bits worth of your memory, all 4 gigabytes of your memory, you can get that big a number. It happens to be a 4-bit int, is really what it means. Yeah, good question. Why they didn't do it int here, I'm not sure, but I guess that's the standard is it's going to be a size t. On your processor, size t happens to be 4 bytes, which means we can address any value. Yeah?
Could this then be extended to count the length of an array of any type?
This could count the array of any type, but arrays generally don't have null termination. So you would need to pass in like the length, and then what's the point? So you don't necessarily, so it couldn't quite work in that way. Like you need to keep track of that when you're making arrays itself. What other question do you have about this stuff? For assignment 3, you're going to write a function called printf. This is probably the most used function in all of C, right? You guys are going to write it. You know, cout is for cout is what you do for C++ or print line or in Java or whatever, or system.out.println. Printf is the one for this. One interesting thing about this. Notice printf here. How many arguments are we passing? 1, 2, 3 for this one. How about this one? 1, 2, 3, 4. Or sorry, 1. This all is 1 argument. 2, 3, 4. There's a way in C to make a function that gets multiple argument sizes. Okay, you have to read about standard arg when you're doing the next assignment. Okay, so you're gonna have to start thinking about reading about that and how to deal with that. Printf is interesting. I think you guys will have fun writing it. You are also in lab this week going to learn how to use the debugger. And learning the debugger is key to making your printf function, because once you learn how to use the debugger, you can actually dig in and go, okay, what's happening here? And you don't have to rely on like a tiny little light blinking on your Pi. Okay, you will eventually have to rely on that when you're trying to test it on your Pi. But in the meantime, we're going to show you how to use a simulated debugger, which simulates most of what the Pi does except for the pins and so forth. Okay, what questions do you have? All right, we'll see you guys Friday or in lab.